We now look at an example of implementing this concept of bar delta filtering using the equivalent circuit model that we've been using all along, the enhanced self-correcting cell model, to illustrate it. We'll start by looking at the overall pack average or bar filter, and then we'll look at the individual cell filters or the delta filters. We are going to have a state that estimates state of charge and the diffusion currents and the hysteresis voltage. And furthermore, we're also going to include a current sensor bias, such as we described a couple sections ago in our state equation, that allows us to track that for the entire pack as well. And actually, what's really nice about the approach of this current sensor bias with the bar delta filtering is that there's only one current sensor in the pack, and so having only one bias estimate in the pack makes sense rather than having a bias estimate for every cell, which would not make sense. We're going to implement a single sigma point Kalman filter for the bar filter. That means that we need to have a model for the state equation and the output equation of the bar filter. And we haven't really addressed how to do that yet, so let's see an example using state of charge as a basis for the example. This is for a single cell, the state of charge equation. So the state of charge for cell I at time k is the previous state of charge of that cell minus the pack current times delta T divided by the capacity of that particular cell, of cell I. To get a pack average equation, we sum all n of these individual equations and we divide by n. So 1 over n times the sum of all the zki equations is 1 over n times the sum of all of these things on the right side, and then over here, the only thing that's a function of I is q, so it would be 1 over n times the sum of all of those. We define a new notation which makes some of this a little bit easier, and 1 over qi we call q inverse of I, and that allows us to write this as just a straight sum, not as a sum of inverses, which is nice. And then that gives us this equation, that this by definition is the pack average SOC at time k. This by definition is the pack average SOC at time k minus 1. And that by definition is the pack average inverse capacity. And we could even put a time index on there if we wanted to, although here I didn't do that. So we have an equation now for state of charge. That is our state equation for that one particular state. This inverse capacity concept makes the equation simpler. If we're estimating all cells' capacities, then we would probably have this time varying quantity as I mentioned, so we would have a k minus 1 subscript on it just to say what time index we're talking about. None of this considered the current sensor bias. If we do consider the current sensor bias, the only thing it changes is right there. I would put in IK minus the bias estimate. And if I look at all of the individual states of the sigma point Kalman filter, we do the same kind of math, the same approach to all of them. So here is the SOC equation. This here is the diffusion resistor current equation. And here is the matrix for hysteresis, the analog hysteresis. And here is the analog hysteresis itself. All of those work out pretty much as you would expect them to do. We introduce here a new thing, which is an estimate of the pack average resistance and an estimate of the pack average capacity. And we allow these estimates to vary using fictitious noises, just like we did for the current sensor bias, which is kind of an interesting thought. The idea here is we're doing some parameter estimation, some state of health estimation, trying to track a varying capacity and resistance. This is a bit of a preview of the kind of thing that we'll look at in the next chapter in order to estimate how the battery pack is aging. We need an output equation. Our output equation says voltage is OCV plus the analog hysteresis. You could put in the instantaneous hysteresis too if you desired, the diffusion, the IR, and then the sensor noise itself. So that part did not change in any kind of unexpected way. That is the pack average, and that's the process by which we came up with the pack average state equation. Now we have to do the same thing for the individual cell delta filters. At the cell level, we're most interested in estimating state of charge, resistance, and capacity. We could estimate all of the other diffusion currents and hysteresis values, or we could assume that there's no difference between the cell and the pack average for those states. And if we assume there's no difference, we don't estimate them. We just have the pack average filter determine the diffusion currents and the hysteresis, and we have the delta filters estimate only the differences in SOC resistance and capacity. And that's what we'll do here. And all of these are going to factor into determining available power and state of health estimates and things like that, as we'll see in follow-on chapters. So let's consider the delta filter approach to determining cell state of charge. The delta equation looks like this. So delta Z of cell I is equal to the actual Z of cell I minus the average, pack average state of charge. And using the prior equations I've already seen for what this looks like and what that looks like, we plug those in. So we have the delta equals the true minus the bar. The true is the previous truth minus the debiased current reading times delta T Q inverse of I. And then the average is the previous average minus the debiased current estimate times delta T times Q inverse of the pack. We take this minus that and say, oh, that's just delta Z at time k minus 1. It gives us this. And we notice that there is a common factor here of all of those. So I put that in. And then what's left is Q inverse I minus Q bar inverse, which is what we will define to be a delta Q inverse for that cell. All right, so we now have an individual state equation for the delta state for state of charge. Now what's interesting is, okay, this delta capacity here is the difference between 1 over Qi minus 1 over Q bar. And if all the capacities of cells are very similar to each other, this number here, regardless of what Q is, that number is going to be very small. It's going to be almost 0. And because it's almost 0, that means that the update I make to my delta state of charge is also going to be very small. So if I have, one cell is 1% away from the pack average, but all of the capacities are exactly the same, then the delta never changes. It's always 1% away from the pack average. If the delta capacities are not all the same, then I do have to update my delta Z a little bit to account for that, but it doesn't update nearly as quickly as the actual pack average state of charge changes. So I can update delta z at a slower rate. We've said that before, but here the math is kind of proving that out. And we would do that by accumulating the input in between updates. We just keep on adding the accumulation of of current, ampere seconds of current in between updates. If I update it one every n times, then I would update n of those, then I would accumulate n of those, and so forth. An output equation for this particular cell that is suitable for combining with this state equation says, well, the voltage of this cell is equal to the open circuit voltage of the SOC of this cell, which is the pack average SOC plus the delta SOC, plus the hysteresis. Here we're assuming pack average hysteresis is close enough for this cell, minus the diffusion. Oops, I missed an R. There's an R missing, RJ. Minus the hysteresis voltages, hysteresis diffusion voltages. And again, we're assuming those are essentially the same for all the cells. And then minus the IR. Here I've got a delta R filter we'll talk about, so I could include that. And then plus some sensor noise. So that would be a good output equation for a Kalman filter to update this. So I've got a state equation, which is all of that. Oops, not quite that far. So the state equation is all of that, and then the output equation is all of that. Now, in this case, my sigma point Kalman filter for delta z is for a single state, and that's really fast. Remember, the sigma point Kalman filter, I need 2 L plus 1 sigma points, and if L is 1, I don't need only 3 sigma points, so that's a very, very small number. And so this is a very, very fast update. The resistance is updated much like we updated the current sensor bias that we saw in the previous section. This is a preview, again, of parameter estimation that we'll look at more in the next chapter. And we'll actually see some better ways to do this in the next chapter, but for now, this is one way to think about it. We say that the delta of this resistance equals the previous delta plus some fictitious noise. Again, we're not adding this in actually, we're just putting it in the model to give us a covariance of the noise from this value that allows us to update this state. And then that would be a good state equation for the delta resistance, and then the output equation would be voltage equals this OCV of the cell SOC, and then I could use a very simple cell model here of simply an IR model, and I drop all the hysteresis and all that other kind of stuff to make a really, really trivial model of this resistance state changing. And while this is crude, it actually turns out to work pretty well. Now, the dynamics of this delta resistance state are simple and they're linear. The dynamics of the output equation are not linear, but the nonlinearity is only in this OCV curve, so it's quite a simple nonlinearity. So in my experience, a single state EKF works quite well rather than an SPKF, so it's just a little simpler to code and use, and maybe a little bit faster as well. If we want to estimate the capacity, we could use an EKF for this also and come up with a state equation for delta Q inverse for this particular cell is equal to the previous delta Q inverse plus some fictitious noise. The trick is to come up with an output equation that makes sense, because you can't measure, capacity just doesn't figure in the output equation. So what we do is we use a difference between two prior state equations in order to do this. So we say, well, the state equation is zki equals zk minus 1I plus the d-bias current times your capacity, delta t divided by capacity, or delta t times capacity inverse. And then we are subtracting one side of the equation from the other to get 0 equals zki minus zk minus 1I, etc. And so it's kind of a manufactured output equation where I expect 0, but I actually compute some other number. And so the prediction is 0, the computation is the measurement, if you will, and I can use that to update a Kalman filter set of equations as well. So the computation for decay is compared to the known value, and the difference is used to update the inverse capacity estimate. So it's kind of a crude way to do it, and there's concerns and issues and problems with doing it this way. It doesn't work as well as we'd like, and that's the major topic of next chapter is looking at how to estimate capacity. So we do a better job there than here, but here at least is a preview for one method that could be used to estimate cell capacity. So we need, the biggest problem with this method is that I need a really good estimate of present and previous state of charge. And here they come from the pack state of SPKF combined with the cell SPKF. In practice, this is maybe not as good as we need to get really a good estimate of capacity, as we'll see next chapter. The output of the delta filters is computed by combining the average battery pack state with the battery delta states. So the cell state of charge is equal to the pack average state of charge plus the delta state of charge. The cell resistance is pack average resistance plus the delta resistance, and the cell capacity is, remember, the 1 over is needed, so it's 1 over the Q inverse plus the delta Q inverse capacity as well. So this section has introduced or has added detail to the idea of bar delta filtering using the ESC model as a basis, and you could do this for other cell models also. You just have to go through all the steps to compute the average equations and the delta equations. And in the next section, what we're going to do is we're going to look at an example of this running to show that it can actually work quite well.